This is going to be a relatively short video, and I'm going to do a whistle-stop tour through the different aspects of multiple regression, starting with simple linear regression and working through the bits and bobs all the way down to diagnostics and checking your assumptions. Now, I'm not going to go through the R code, and I'm going to have separate videos that go through each of these concepts in a lot more detail. This is literally a nice summary just to kind of get your head around the issues. If you're looking at this for the first time, great place to start. And if you want to just quick refresher, this is a great video to watch. On this YouTube channel, we're creating R programming videos on everything. Okay, first of all, simple linear regression. We're looking at a relationship between, on the x-axis, an explainer variable or an explanatory variable, or sometimes we call it an independent variable, and an outcome variable, right? And we think that one has a relationship with the other, and we think that that relationship is linear, right? So as one goes up, the other one goes up, and it does so in a consistent manner. It's not exponential, it doesn't change, it goes up in a nice straight line. Look, here we've got height is an explanatory variable on the x-axis here, and weight, and this is a data set of women, and weight is the outcome variable. And what we're saying is that as women get taller, it stands to reason that we think that they get heavier, and yes, it does look like there's a relationship between those two things. And that line, the blue line going through the dots are the actual data points, is the best fitted line. That is our model. That is our linear model. Okay, and this is a nice simple model, and we see there's a nice simple linear relationship. I'm not talking at this point about the assumptions that go behind our model. We're going to talk about that a little bit later, but that's just basically the model. Now, there's two things that we can get from this model. First of all, we can ask the question, to what extent is the weight of a woman explained by her height? To what extent is height, and does height really explain weight? That's the one question we can ask. And the other question is we can predict. So we can say, for a given height, what do we expect, using our model, the weight of a woman to be? Now, it might be within the parameters, within the sort of data set that we've got within here, it's between 60 and 72, but you can extrapolate even outside of that range, right? So those are the two things you can do with your linear model. Let's look at the results that we've got on the left-hand side here. And I'm not going to go through everything. You'll sort of see as we go through these various graphs, you'll understand that in a bit more detail the other things. But let's just look at these are the results. This is the results that come from using R programming. Get the same results in a different format using other platforms. Okay, at the top we've got the model itself. Residuals, I'm going to talk more about residuals a little bit later on in this video, but essentially this is this is the distribution of the residuals. We expect them to be normally distributed, and a couple of other assumptions about them. We'll come back to that. Next is our intercepts. The top, the coefficients, the top is our y-intercept. The y-intercept is very often meaningless because it is the point at which the line will cross the y-axis, and that is when the x-axis is equal to 0. Well, there's no such thing as a zero height woman, and so what is the weight of a woman whose height is 0? It's a meaningless thing, but it's in the model, so we ignore that in this particular model. Height, however, is a coefficient that we're interested in, and that is the slope. How steep is this curve? And basically that 3.45 tells us that for every increase in incremental height, and I think this is height in inches and weight in pounds, for every inch that you go up in height, on average you go up 3.45 pounds in weight. So that's the relationship. On the right-hand side, you can see the p-values for both of those coefficients are statistically significant, so that's a good thing. The numbers at the bottom, the ones that I want to draw your attention to, is the one at the very bottom, the F statistic. If that has got a low p-value, it tells us that at least one of the explainer variables in our model does have explanatory power of the outcome variable. In this case, there is only one explanatory variable, but down the line you'll see we have more than one. P-value very small, so that keeps us happy. We've got 2 r squared. On the left-hand side, multiple r squared, and on the right-hand side, adjusted r squared. If it's a simple model, in other words, there's just one explanatory variable, as in this case, we always use the multiple r squared, the one on the left, and this is 0.99. And what that means is that 99% of the weight of a woman can be explained by her height. That's the explanatory power of this model. If we had more than one explanatory variable in our model, we wouldn't use the multiple r squared, but we would shift over to the right-hand side and use the adjusted r squared figure instead. Right. If you've got the basics, if you've got that, we're good to go. Boom, shakalaka. Let's move on. let's add in another numeric variable, right? So now we've got trees, and we've got the volume of trees, so how much wood there is in a particular tree, and that can be explained by the girth of the tree and the height of the tree. So we've got two explanatory variables, not just one. Our model looks very much the same. At the top, we've got volume. It's explained by girth plus height. So if you're working in R, you just put a plus and you add in the extra variable, and that's how you build up your model. We're assuming, for the sake of this particular model, that there's no interaction between these two things, and we're going to talk about interactions in just a minute. But while we're explaining things one step at a time, one concept at a time, don't worry about interactions. We're not going to talk about residuals again. And what I want to draw your attention to, and again, the intercept is meaningless. A tree with zero girth, we don't worry about the volume, for example, so ignore the y-intercept. But the coefficient, the slope coefficient for girth and for height are in the results here. For girth, and they're both statistically significant, you can see that on the right-hand side, so happy days. For girth, as the girth of the tree increases by 1 unit, the volume increases by 4.7 units, and as the height of the tree increases by 1 unit, the volume of the tree increases by 0.33, so it's a smaller amount. So both of those are statistically significant. The F statistic has got a low p-value, so we're happy that the model is valid overall. And the multiple R squared on the left-hand side we ignore, because now we've got an extra variable in. This is multiple regression, not simple regression. So we shift over to the right-hand side and we look at the adjusted R squared, which is 0.94. So 94% of the volume, of the change in volume, can be explained by changes in both girth and height as a combination. Okay, so that's what the adjusted R square means, and that's a really useful thing. Okay, so in this particular example, we added a numeric variable as an additional explanatory variable. So this is now multiple regression. What if we added a categorical variable? And in this case, it's a categorical variable with two categories. Let's look at the graph on the right-hand side. This is data about cars. We've got highway fuel efficiency is the outcome variable, and engine size is one of our explanatory variables. You can see it on the x-axis. And the other explanatory variable is drive. Is it a four-wheel drive or a two-wheel drive car? So we've got two explanatory variables. One of them is numeric, one of them is categorical. And of course, we can plot that. We plot all the lines. We draw our model, and we've disaggregated by drive. Red, four-wheel drives are red, and two-wheel drives are blue. What I want you to notice in this particular diagram is that these two lines are parallel. And what does that mean? And it's quite important to take note of this. What does that mean? It means that as engine size increases, the slope of four-wheel drive cars and the slope of two-wheel drive cars doesn't change. In other words, engine size doesn't interact or affect or have any kind of impact on the extent to which on the other variable, and vice versa. So these two variables don't interact with each other. And that's important, and we're going to see why that's important in a minute when we look at variables that do interact. So looking at an example of where they don't interact will help you understand an example of where they do interact. Okay, so I just wanted you to take note of that fact, that as engine size increases, it makes no difference if it's a two-wheel drive or a four-wheel drive. The slope of the curve remains the same. Let's have a look at the results on the left-hand side. The coefficient, the intercept coefficient, ignore. Displacement, which is really engine size in this particular data set, displacement, minus 2.84. So all else being equal, in other words, if all the other variables kept constant, if you were to increase the engine size by 1 unit, the fuel efficiency would decrease because it's minus 2.8, so it's a negative slope, minus 2.84. The fuel efficiency would decrease by 2.84. Now, this is another thing that you just need to pay attention to because it might be a little bit confusing if you haven't been exposed to this before. But drive, here we've got drive is the variable, is the categorical variable, and we've just got two there. So that must obviously reflects two-wheel drives, and we don't have a coefficient for four-wheel drives. The reason is I'm using four-wheel drives in this particular example as the base or the reference category, and we're comparing two-wheel drives to four-wheel drives. So remember if we just reflect back on displacement, right? So the engine size, we were saying for every increase in engine size from 2 to 3, 3 to 4, 4 to 5, 5 to 6, for every one of those incremental increases, right, the fuel efficiency would decrease by 2.86. And because it's a numeric variable, there was multiple opportunities, multiple possible units that it could change. In this categorical variable, there is only one possible change. It's from four-wheel to two-wheel drive. Or you could do it the other way around. It wouldn't really matter. There's only one incremental change. And so where we see drive 2 is 4.94, it means if all else being held equal, if we moved a car from being a four-wheel drive to being a two-wheel drive, then there would be a gain in fuel efficiency of 4.94. I think it's miles per gallon. Okay, we are talking about a change. We're talking a change from 4 to 2, and that would be associated with a gain of, on average, 4.94. In other words, another way of looking at it is these two parallel curves, the distance between them is about 4.94 on average from left, the distance between these two lines. Okay, hope that makes sense. Let's keep going. And again, the usual, we're looking at adjusted R squared 7.73. In other words, 73% of highway fuel efficiency can be explained by a combination of engine size and drive. Incidentally, and I'm not going to do it in this example, if we added drive at the top, displacement, which is engine size, plus drive, suggesting that we don't think that there's an interaction, and it doesn't look as if there is one. If we changed that, if we wanted to test for an interaction here, if we thought there might be some interaction that we're not seeing, we changed that plus to a times, then it would add in an interaction term in our results, and we would look for an interaction between these things. I'm not going to do it now, but I can tell you, because I've done it before, that if you ask for an interaction term, which we're going to look at in a second, firstly, it's not statistically significant. So it doesn't give a p-value of less than 0.05. And secondly, it doesn't change the adjusted R squared at all. And so adding that to our model doesn't add anything to the explanatory power of the model at all. And so we don't add it. And that's just a quick lesson. It's the beginning of a lesson in how do we decide what variables and which interactions to include in our model, all right? Because very often there's many, many variables we could consider. And there's two ways that we kind of think about that. Well, there's multiple ways that we think about that. But the one is that we start with a simple model that we know where we're comfortable with, and then we add additional variables one at a time until adding and as we add each additional variable, the expectation is that the model is improved. Like we see a better model with the extra variable. So the explanatory power, the adjusted R squared goes up, the p-values, the significance improves. And so we get a better and better model as we add additional variables. And we do that until we get to a point by adding additional variables, there's no improvement. And then we sort of say, well, then if adding that in variable doesn't translate into any improvement, we don't add it. And what we're left with is the model that we've got. You can also do it the other way around. You can start with all of your variables in there and remove them one at a time. And there are automatic ways of doing this. One of the things that you can do, there's this a K-care. I don't know how you pronounce it. It's A-K-A-I-K-E. It's basically an AIC. It's a measure of the strength of a model based on the extent to which it is there's a good model fit, but it's not too complex. In other words, it looks at all possible combinations of variables, all possible models that you could create with this data, and it penalizes models that have too many variables, credit to models that have a better fit. And by doing that, it identifies the model that has the best score, and so you can that's the model that you'll use. In the long video where I deal with this, I actually walk through an example, and you can look at that more closely in your own time. But here we go. So that is adding an additional categorical variable. Let's take a look at the idea of interactions. So this is where, and what is an interaction? An interaction happens when the relationship between one explanatory variable and an outcome variable is affected by a third explanatory variable, right? So the best way to understand that is to look at a nice example. Here we've got fuel efficiency explained by weight of cars. This is actually from a different data set. Fuel efficiency explained by the weight of cars. Fuel efficiency is the outcome variable on the y-axis. Weight of cars is the explanatory variable on the x-axis, and we can see that as cars get heavier, fuel efficiency drops off. Fine, that makes perfect sense. If we look at our model, we can see that weight is statistically significant, and for every increase in unit of weight, we have a decrease of fuel efficiency by 5.3. Fine. The F statistic has a small p-value, happy days. and the adjusted R squared, well, no, this is a simple model, so the multiple R squared is 0.75, which means that 75% of the fuel efficiency can be explained by change in fuel efficiency can be explained by change in weight of car. Right, happy days. What happens if we introduce another variable which we think interacts with the weight of the car? Let's have a look at that. Here we go. So transmission, is it an automatic or a manual car? This is the exact same data points, but now we've colored them by transmission. The blue dots are the manual cars and the red dots are the automatic cars. And we can see that the linear model within those two groups is different, right? So the relationship between weight and fuel efficiency depends on whether or not you're talking about a manual or an automatic car. So if you ask the question, how does weight affect fuel efficiency? The answer to that question is, well, it depends. It's dependent on which kind of car you're talking about. Is it automatic or manual? So there's an interaction between these variables, right? And if you can understand that conceptually and understand that in the context of this plot, all of the results will make perfect sense. And this is what we call interactions. So at the top, you can see the formula that I'm using, MPG, which is fuel efficiency, miles per gallon, explained by WT, which is weight, and then AM, which is transmission. I've got a times there instead of a plus. And that means that I'm not just adding in an additional explanatory variable, but I'm adding in that explanatory variable plus any interactions that it would have with the first variable, right? So that's what the times is there. Data equals dot, that's just using the whole data set. Okay, residuals, we're going to come back to residuals and the assumptions around that later. So, hang in there. Here are our coefficients. The intercept we're going to ignore because a car of weight 0 doesn't exist. So it's not a valid idea in this particular analysis. But here are our other coefficients. Before we look at them, just as a matter of routine, I always look at the F statistic at the bottom, small p-value, happy days, something about this model is working. The adjusted R squared, because there's multiple variables in here, so we look at the adjusted R squared is 0.81. Interesting. So we have that's quite high. So fuel efficiency, change in fuel efficiency can be explained by weight of car and transmission. It can explain 81% of the change in fuel efficiency can be explained by the weight of car and transmission and the interaction between the two. Happy days. The other thing to take note of, and I'm just doing this as a routine to get you into the habit of thinking like this, is look at the statistical significance. All of our coefficients are statistically significant, so we're happy that they're in there for the most part. Okay, so what are the coefficients? The weight coefficient minus 3.4. So basically, all else being kept equal, right? So if you keep transmission constant, with every increase in the weight of the car of 1 unit, there will be a 3.78 or 3.8 decrease in fuel efficiency. Okay, and that makes sense. We can see there's it's a downward sloping trend. Happy days with that. AM manual, similar to the example that we looked at earlier where we had categorical variable added in here. Transmission manual means that all else being kept equal, if we simply moved a car from being automatic to manual, okay, there would be an increase in fuel efficiency of 14.8. Right, so again, happy days. Now, the last line is the interaction of the weight of car with AM manual. And what does that mean there? It means that manual cars, with respect to every incremental increase in 1 unit of weight, there would be a decrease in fuel efficiency of 5.3 or 5.29 compared to if the car was automatic. Okay, I know that's quite a lot to get your head around, but if you think that sentence through in the context of the plot that's on the screen, it'll make sense. So that's the interaction of weight and transmission on fuel efficiency. All right, now I want us to talk about the assumptions that we make when we do multiple regression or regression analysis. We make certain assumptions about our data, and we need to check that those assumptions are in fact valid. Right, so let's just talk about what the assumptions are. The first assumption is that there's a linear relationship between the explanatory variable and the outcome variable, right? That's the first assumption. The next 3 assumptions really are about the residuals. And the graph on the left helps us understand what we mean by residuals. Residuals are the distance between the actual data point, so the black dots, and the fitted value for that same x-axis point, right? So it's the red line, basically. Like if you look at those red lines, the blue line is the model, the black dots are the actual data points that we've got in our data set, and you don't expect all of our data points to sit exactly on the model. They're all going to kind of, because we live in the real world, they're all going to be kind of outside of the model to an extent, and the extent to which there's an error, we call that the residual value, right? The difference between the model and the actual values that we've got. Okay, I'm carrying on about this a little bit because understanding what the residual is extremely important for a couple of the things that we're about to talk about right now. So we've got these residual values all the way across from left to right, from top to bottom. Fine. We make certain assumptions about those residuals. Remember, our first assumption is that there's a linear relationship between the explanatory and the outcome variable. The next three assumptions are about the residuals. The first is that the residuals themselves are normally distributed. Okay? So the residuals are normally distributed. In other words, if you look at the values of all of those residuals, and you think, if you think about what a normal distribution is, it's on either edge, in terms of the low and the high values, they're small, and most of the values are kind of in the middle, right? So on this graph, the very, very small residuals, there should be a few of those. There should be a few that are very high, and most of the residual values should be sort of in the middle, and that would be a normal distribution. We're going to talk about how to check that in just a second. Okay. So assumption one about the residuals is that they're normally distributed. Assumption number two is that they're homoscedastic. Now, what that means is that the variance between the residuals as you go across the fitted values is evenly distributed, so that that we don't have some residuals on one side of the curve where there's large residuals, and at the other side of the plot the residuals are very small, or some kind of pattern. We don't want any pattern. We want it to be random. Okay, and then the third and final assumption that we make is that the residuals are independent. In other words, that the error that we see at this point in time isn't influenced by the error that we saw at a different point on our plot. And the best way to understand that is to think about a time series analysis, where if you've got multiple participants and they're all getting something measured about themselves at different points in time, at the various points in time, I'm the same person as I will be at the next measurement. And so the error for me as a data point going forwards, the error at that point isn't independent of it. Now, let's say they're talking about the extent, how quickly we're growing. Well, when you measure my growth in 2 years' time and then in 2 years after that, those values aren't independent. It's the same person going through. There may be I might have some genetic disposition or nutritional reason why I grow faster than the next person. So my values along the timeline are all dependent and connected to, and not independent, let's say, of its previous values. So those values are not independent of each other. So time series analysis is a good example of where your residuals are not independent. Okay, so those are your three residual assumptions about the residuals, and your one assumption about your exposure and your outcome variable being linearly related. How do we check these things? Easy peasy lemon squeezy. Don't worry, we can do that. The first assumption about the linear relationship between the exposure and the outcome variable, it's reasonably straightforward, and that is that you can visually look at it. So we visually look at the relationship. It looks linear. We're not seeing any sort of massive curve, so that's a good sign, tick. The next thing we can do, and that's the plot on the right-hand side, is we plot the residuals versus the fitted values. So for any particular x-axis, any one of these black dots, there is the residual, which is the red line, okay, and then the fitted value is what the model would predict, which is the residual is the length of the red line. The fitted value is the y-axis, or the outcome variable predicted value for that same data point. So whatever, if we mapped out from the blue line against the y-axis, what is the expected value at that point? So the difference between, so here we've plotted the y-axis in this plot on the right-hand side are the residuals versus the fitted values. Now, what you need to know about this plot here is you expect it to be random. You expect there to be as many dots above and below the line. You don't expect any pattern. If there's a pattern, it means there's something happening in the data which we need to look at a bit more closely, right? So you want this to be random. And if that's the case, it's a good sign of linearity. Okay, so for all of these assumptions, there are visual checks that give us a sense of things are fine here. If things aren't fine, then there are statistical tests that you can do that confirm that these plots are in fact that assumption is or isn't met. Okay, got it? So first assumption, and I'm going to come back to that. I'm going to come back to the statistical tests that you can do. So first assumption is that these things are linear. We look at the plot. We look at the residuals versus fitted. Happy days. Okay. The next assumption, and by the way, here are examples of it not being random. Right. So we can see examples. There's a funnel on the right. We've got a U shape on the left. If we saw these, that would be an alarm that we really need to do statistical tests to demonstrate or identify or dig deeper with respect. In fact, if we saw this, we would know for sure that there's a problem. I mean, we wouldn't even need to do statistical tests. I would tell you that this, something is wrong. The next assumption is that the residuals are normally distributed. Two ways to do that. Firstly, we can plot a histogram. Again, this is subjective, right? We look at that histogram. Well, is that a normal distribution? What are the sizes of the buckets? Do we have enough data points? Not sure. But it's if it was a very nice histogram, that might kind of be a big tick and we'd be smiling. On the right-hand side, we've got a QQ plot. Okay, these are quantiles. Now, what is a quantile? Quantile is a point in your data that divides the data set into two probabilities. So the median divides it into 50-50. And you've got quantiles all the way along. So quartiles are dividing it into 4, into 25%, 25%, 25%, 25%, etc., and you can get smaller and smaller increments. If you take a normal distribution and you know what those quantiles are, and you compare it to the distribution of the residuals, you can plot those quantiles against each other. And if it is the case that your residuals are normally distributed, you will see those plot points going in a nice diagonal line like you're seeing over there. So it is, again, a subjective visual clue as to what's happening, but it could be quite comforting if it makes a really nice diagonal line. You could say, look, we're happy enough. Again, there is a statistical test that you can do that I'm going to come back to that can check that. So second assumption that the residuals are normally distributed, we look at that. The third and fourth, the visual tests for both of them really are looking at this residuals versus fitted values. So let's just go through them quickly. Homoscedastic, that is that there is the variance in residuals is equally distributed across all the fitted values. If that wasn't the case, there would be clumping. There would be a pattern. In fact, that funnel shape is a typical pattern. This funnel shape on the right is a typical pattern where this assumption is not met. For example, if there is some sort of shape, some sort of clumping, it means let's dig deeper. Let's do the statistical tests to check independence again. And let me just give you an example of where things wouldn't be independent. Here's the example that I was talking about earlier, where we've got individuals in a sort of cohort study going forward over time, being tested at 8 years, 10 years, 12 years, and 14 years, but the same person is being tested along those lines. So the residuals for a particular person along those lines wouldn't be independent. It would be somehow dependent on the previous ones. Again, if there isn't independence, we would see that there would be a pattern of some description in this residuals versus fitted values. So this particular plot is very, very useful because if it is random, if it is a good plot, it ticks a lot of boxes with respect to our model. Now, what I want to do quickly now, I want to talk about the statistical tests that we would do just to check these things. Okay, and I'm going to go into R. Let's just go into R quickly, and I'm not going to go into a lot of detail, but it's going to be here in assumptions. I need to get this outline. The statistical test that we would do for whether it's a linear relationship is the Harvey-Collier test. And I will just tell you, I'm not going to go through all of the results for it, but I'm just going to remind you of this fact. The null hypothesis for this is that there is a linear relationship. In other words, and this is quite unusual, but we're looking for a high p-value, not a low p-value, because we do not want to reject the null hypothesis. Okay, that's quite important, and we're going to see that again when we look at the statistical test for are the residuals normally distributed. It's the Shapiro test. Again, we're looking for a high p-value. If the p-value is high, we don't reject the null hypothesis, and the null hypothesis is that the residuals are normally distributed. Okay, and again, for the residuals being homoscedastic, we do the Bruce-Pagan test. Again, a high p-value is what we're looking for because the null hypothesis is that the residuals are homoscedastic. I know that is a little bit unusual for us to be doing in stats. Okay, and then finally, the residuals are independent. Here we use the Durbin-Watson test, and we look at the DW statistic, and if that is close to 2, it means that there is independence. In this case, it's far away from 2, which you would expect because this is the example of where we don't think that there is independence. We think that there is dependence. The last thing that I'll just quickly talk about is collinearity. And collinearity happens when you've got more than one explanatory variable. Well, it's collinear if there's 2 of them, and multicollinearity if there's multiple of them, which are obviously correlated with the outcome variable, but also correlated with each other. And so you might be with more than one variable explaining the same thing. You could have the same story being told by more than one variable. And when that happens, you may want to consider removing one of them from your model. Now, whenever you make that decision, it should be based on your expert knowledge of the subject and your understanding of the data and your understanding of the relationships between the data and the outcomes, so that you can make an informed decision as to whether or not that variable should stay or go. There are times when, even if there is correlation between 2 explanatory variables, you should keep the explanatory variable in the model. An example is when there is confounding. So confounding, let me quickly explain what confounding is. It's an alternative explanation for an outcome. Quick example, we might see that there is a positive correlation between ice cream sales and shark attacks. Right? Ice cream sales go up, shark attacks go up. Now, we don't want to make the mistake of thinking that that is a causal relationship. And the reason and the way we get our heads around this is we say there is a confounding variable, a third variable that is associated both with ice cream eating and with shark attacks, but not on the causal pathway between them, and that is hot weather. So in hot weather, people eat more ice creams, but also in hot weather, people swim in the sea and are more likely to get eaten by a shark. So ice cream eating is associated with hot weather. Hot weather is associated with shark attacks. And so you've got hot weather and ice cream eating are both positively correlated, but you want them both in the model because they control for each other. Okay, so I think we've covered a lot. I think we've covered just about everything that I would want to in a quick overview. Obviously, there's a lot more detail that you can go into in the individual videos that I've got on the screen. At the moment, at the top, you'll see there's a little card that you can click on. That'll take you to a resource library where you can get a free download of all the PDFs for all of these lessons and the data. I only use data that is built into R, so of course you can work along with and do the examples. Okay, I hope that was useful. I recommend watch the entire series and you'll get your head around linear regression. Okay, thanks for watching. Take care. Bye.